My dear students of Standard 10, Zankar Educational Series welcomes you. Let's enjoy learning Science and Technology Part 1. Chapter 1, Gravitation. We all know that the gravitational force is a universal force and it acts not only between two objects on the earth but also between any two objects in the universe. So let's see what is meant by gravitation. The phenomenon of gravitation was discovered by Sir Isaac Newton. He discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downward and not at an angle to the vertical. Why do they not fly off in a horizontal direction? So he came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is the vertical direction at the position of the apple, and thus the apple falls vertically downwards. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the earth, can it also act on objects at even greater heights, much farther away from the earth? Yes. To find this, let's see about force and motion. We know that a force is necessary to change the speed as well as the direction of motion of an object. So let's see about circular motion and centripetal force. Tie a stone to one end of a string and take the other end in your hand and rotate the string so that the stone moves along a circle. As long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle, and are applying a force towards it. The force stops acting if we release the string. In this case, the stone will fly off along a straight line, which is the tangent to the circle at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time. Thus, a force acts on any object moving along a circle and it is directed towards the center of the circle, and this is the centripetal force. The moon, which is the natural satellite of the earth, goes round it in a definite orbit, and the direction of motion of the moon as well as its speed constantly changes during this motion. That means there must be a force which is exerted on the moon, and this force must be exerted by the earth, which attracts the moon towards itself. Similarly, the sun must be attracting the planets, including the earth, towards itself. Then Kepler's laws. By the 16th century, a lot of data were available about planetary positions and motion. Johannes Kepler studied this data and noticed that the motion of planets follows certain laws. So, Kepler's first law: the orbit of a planet is an ellipse with the sun at one of the foci. Here we can see the elliptical orbit of a planet revolving around the sun and the position of the sun indicated by S. An ellipse is the curve obtained when a cone is cut by an inclined plane. It has two focal points. The sum of the distances to the two focal points from every point on the curve is constant. So, if F1 and F2 are two focal points of the ellipse, and if A, B and C are 3 points on the ellipse, then AF1 plus AF2 is equal to BF1 plus BF2 is equal to CF1 plus CF2. Then Kepler's second law. The line joining the planet and the sun sweeps equal areas in equal intervals of time. The straight lines AS and CS sweep equal area in equal interval of time. That means the area ASB and the area CSD are equal. Then Kepler's third law. The square of its period of revolution around the sun is directly proportional to the cube of the mean distance of a planet from the sun. Thus, if r is the average distance of the planet from the sun and t is the period of revolution, then t square is directly proportional to r cube. That means t square upon r cube is equal to constant is equal to k. Then Newton's universal law of gravitation. According to this theory, every object in the universe attracts every other object with a definite force, and this force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. So, here we can see two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies is written as F is directly proportional to m1 m2 upon d square, or F is equal to g m1 m2 upon d square. Here g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. But if the bodies are not spherical or have irregular shape, then the direction of force is along the line joining their centers of mass, and d is taken to be the distance between the two centers of mass. So from this equation, we can say that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. In SI unit, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. The unit of g in SI is Newton meter square per kg square, and the value of g is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Then uniform circular motion, that is magnitude of centripetal force. Consider an object moving in a circle with constant speed. Such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle, and this is centripetal force. If m is the mass of the object, v is its speed, and r is the radius of the circle, then this force is equal to F is equal to mv square upon r. If a planet is revolving around the sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards the sun must be F is equal to mv square upon r, where m is the mass of the planet, v the speed, and r is the distance from the sun. The distance travelled by the planet in one revolution is the perimeter of the orbit, that is 2 pi r, where r is the distance of the planet from the sun. Time taken is the period of revolution, that is t. So V is equal to distance travelled upon time taken is equal to 2 pi r upon t. F is equal to mv square upon r is equal to m 2 pi r upon t bracket square upon r is equal to 4 m pi square r upon t square. Multiplying and dividing by r square, we get F is equal to 4m pi square upon r square into r cube upon t square. According to Kepler's third law, t square upon r cube is equal to k. Therefore, F is equal to 4m pi square upon r square k. But 4m pi square upon k is constant. Therefore, F is directly proportional to 1 upon r square. Thus, Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in nature, but it controls the universe and decides its future. And this is possible because of the huge masses of planets, stars, and other constituents of the universe. Then Earth's gravitational force. The Earth attracts every object near it towards itself because of the gravitational force. The center of mass of the Earth is situated at its center, so the gravitational force on any object due to the Earth is always directed towards the center of the Earth. Because of this force, an object falls vertically downwards on the Earth. Similarly, when we throw a stone vertically upwards, this force tries to pull it down and reduces its velocity. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downward towards the center of the Earth under its influence. Then Earth's gravitational acceleration. The Earth exerts gravitational force on objects near it, and according to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the Earth on a body results in its acceleration, and this is acceleration due to gravity, which is denoted by g. Acceleration is a vector. As the gravitational force on any object due to the Earth is directed towards the center of the Earth, the direction of the acceleration due to gravity is also directed towards the center of the Earth, that is vertically downwards. Now, value of g on the surface of the Earth. The law of gravitation gives F is equal to gmm upon r square, where capital M is the mass of the Earth, small m is the mass of the object, and small r is the distance of the object from the center of the Earth. F is equal to mg. From 3 and 4, mg is equal to capital G into capital M into small m upon r square. Small g is equal to capital G capital M upon r square. If the object is situated on the surface of the Earth, small r is equal to capital R is equal to radius of the Earth, and thus the value of g on the surface of the Earth is small g is equal to gm upon r square. The unit of g in SI unit is meter per second square. Mass of the Earth is 6 into 10 raised to 24 kg and radius of the Earth is 6.4 into 10 raised to 6 meter. Using this, we get g is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 bracket square is equal to 9.77 meter per second square. This acceleration depends only on the mass m and radius r of the earth, and so the acceleration due to gravity at a given point on the earth is the same for all objects. It does not depend on the properties of the object. Now variation in value of g. First, change along the surface of the earth. The value of g is not same everywhere on the surface of the earth. The reason is that the shape of the earth is not exactly spherical, and so the distance of a point on the surface of the earth from its center differs somewhat from place to place. Due to its rotation, the earth bulges at the equator and is flatter at the poles. The radius is largest at the equator and smallest at the poles. The value of g is thus highest 9.832 meter per second square at the poles and decreases slowly with decreasing latitude, and it is lowest, that is 9.78 meter per second square at the equator. Then change with height. As we go above the earth's surface, the value of small r increases and the value of g decreases. However, the decrease is rather small for heights which are small in comparison to the earth's radius. That means if an aeroplane is flying at a height of 10 kilometers above the surface of the earth, its distance from the earth's surface changes from 6400 kilometers, that means the radius of the earth, to 6410 kilometer, and this change in the value of g due to it is very negligible. On the other hand, when we consider an artificial satellite orbiting the earth, we have to take into account the change in the value of g due to the large change in the distance of the satellite from the center of the earth. Then change with depth. The value of g also changes if we go inside the earth. Actually, according to the value of r in equation 5, one would think that the value of g should increase as per the formula. However, the part of the earth which contributes towards the gravitational force felt by the object also decreases, which means that the value of capital M to be used in equation 5 also decreases. As a combined result of change in r and capital M, the value of g decreases as we go deep inside the earth. On the moon, the value of g is about 1/6 of the value of the earth. As a result, using the same amount of force, we can jump 6 times higher on the moon as compared to that on the earth. Then mass and weight. Mass is the amount of matter present in the object. The SI unit is kg. Mass is a scalar quantity and its value is same everywhere. Then weight. Weight is the force with which the earth attracts the object. So weight W is equal to F is equal to mg, where g is capital G into capital M upon capital R square. Weight being a force, its SI unit is Newton and force is a vector quantity. As the value of g is not same everywhere, the weight of an object changes from place to place, though its mass is constant everywhere. Colloquially, we use weight for both mass and weight and measure the weight in kilogram, which is the unit of mass. So our weighing machines tell us the mass and two scale balances in shops compare two weights, that is two masses. Then free fall. We know that the force of gravity due to the earth acts on each and every object. When we were holding the stone in our hand, the stone was experiencing this force, but it was balanced by a force that we were applying on it in the opposite direction. As a result, the stone remained at rest. Once we release the stone from our hands, the only force that acts on it is the gravitational force of the earth, and the stone falls down under its influence. Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in a free fall. In free fall, the initial velocity of the object is zero and goes on increasing due to the acceleration due to the gravity of the earth. During free fall, the frictional force due to air opposes the motion of the object, and a buoyant force also acts on the object. Thus, true free fall is possible only in vacuum. For a free falling object, the velocity on reaching the earth and the time taken for it can be calculated by using Newton's equations of motion. For free fall, the initial velocity u is 0, the acceleration a is equal to g, and thus we can write the equations as v is equal to gt, s is equal to 1 upon 2 gt square, v square is equal to 2gs. For calculating the motion of an object thrown upwards, acceleration is negative as it is opposite to the velocity and is taken to be minus g. The magnitude of g is the same, but the velocity of the object decreases because of this negative acceleration. The moon and the artificial satellites are moving only under the influence of the gravitational field of the earth, and thus they are in free fall. The value of g is the same for all objects at a given place on the earth. Thus, any two objects, irrespective of their masses or any other properties, when dropped from the same height and falling freely, will reach the earth at the same time. But when we drop a feather and a heavy stone at the same time from a height, they do not reach the earth at the same time. The feather experiences a buoyant force and a frictional force due to air, and therefore floats and reaches the ground slowly later than the heavy stone. The buoyant and frictional forces on the stone are much less than the weight of the stone and does not affect the speed of the stone much. But scientists performed experiment in vacuum and showed that the feather and stone indeed reach the earth at the same time. Then gravitational potential energy. The energy stored in an object because of its position or state is potential energy. It is relative and increases as we go to greater heights from the surface of the earth. We had assumed that the potential energy of an object of mass m at a height h from the ground is mgh, and on the ground it is 0. When h is small compared to the radius r of the earth, we can assume g to be constant and can use the formula mgh. But for large values of h, the value of g decreases with increase in h, and for an object at infinite distance from the earth, the value of g is 0 and earth gravitational force does not act on the object. So it is more appropriate to assume the value of potential energy to be 0 there. Thus, for smaller distances, that is heights, the potential energy is less than 0, that is negative. When an object is at a height h from the surface of the earth, its potential energy is minus gmm upon r plus h, where capital M is the earth's mass and capital R is the radius of the earth. Then escape velocity. We have seen that when a ball is thrown upwards, its velocity decreases because of the gravitation of the earth. The velocity becomes zero after reaching a certain height, and after that the stone starts falling down. Its maximum height depends on its initial velocity. According to Newton's third equation of motion, v square is equal to u square plus 2as. Thus, higher the initial velocity u, the larger is the height reached by the ball. The reason for this is that the higher the initial velocity, the ball will oppose the gravity of the earth more, and larger will be the height to which it can reach. The value of g keeps decreasing as we go higher above the surface of the earth. Thus, the force pulling the ball downward decreases as the ball goes up. If we keep increasing the initial velocity of the ball, it will reach larger and larger heights, and above a particular value of initial velocity of the ball is able to overcome the downward pull by the earth and can escape the earth forever and will not fall back on the earth. It is escape velocity. An object going vertically upwards from the surface of the earth having an initial velocity equal to the escape velocity escapes the gravitational force of the earth. The force of gravity being inversely proportional to the square of the distance becomes zero only at infinite distance from the earth. This means that for the object to be free from the gravity of the earth, it has to reach infinite distance from the earth. That means the object will come to rest at infinite distance and will stay there. For an object of mass m on the surface of earth, kinetic energy is equal to 1/2 mv square ESC, potential energy minus gmm upon r, and total energy E1 is kinetic energy plus potential energy, that is 1/2 mv square ESC minus gmm upon r. Now at infinite distance from the earth, kinetic energy 0, potential energy minus gmm upon infinity is equal to 0. So total energy E2 is kinetic energy plus potential energy is equal to 0. So the spacecrafts which are sent to the moon or other planets have to have their initial velocity larger than the escape velocity so that they can overcome Earth's gravitational attraction and can travel to these objects.